So the object of nucleophilic addition is going to be that we're starting with something that has a double bond. So let's say this, and we're going to add some type of hydrogen and something else, and we're going to get a single bond with this combined. That H is going on this carbon here, it's not shown. Okay, so how do we go about doing this? Well, if we have this double bond, this double bond can actually act like a nucleophile because, it's basically made of electrons, right? So it can actually kind of jump out and attack things. And that's what it's going to do here. It's going to jump out and attack this H because this is partial positive and this is partial negative. So electrons in the double bond are going to attack the partial positive, right? And this bond is going to break. These electrons are going to go to bromine. Okay, so this is going to get us a carbocation because we're taking those two electrons in the double bond and we're saying we're going to make a bond with this hydrogen. The question is, which carbon are we going to put it on? Well, one carbon has to have the hydrogen, the other carbon has to have a carbocation, right? Where's the better place to put a carbocation? Here or here? The first one, because it's tertiary, while the other one is primary. As a reminder, more carbons or more substitution is better because when we put this carbocation on, these three guys are going to be pushing in electron density and stabilizing that positive charge, whereas that wouldn't happen on the primary one. So the hydrogen goes here, so before we had two hydrogens, right? Now we have three hydrogens. And now we have this Br minus, right? Where is that going to go? It's going to go here. Another nucleophilic attack. And that gets us our product. That looks like that. So that decision that we just made as to where to put the hydrogen and where to put the carbocation, we call that Markovnikov's rule. And this rule says that whatever other thing that's not hydrogen is going to go in the more substituted carbon or the carbon that's bonded to more other carbons. The way I like to think of it is that hydrogen likes to be with its friends because there's more hydrogens on this carbon than on this one. Or there were to begin with. There were two hydrogens over here, there were no hydrogens over here. So therefore the hydrogen wanted to be with its buddies and the bromine ends up on the other one. But you can think of it like the bromine is on the more substituted one, if that's easier for you. I want to show you one specific kind of nucleophilic addition, and this is called hydration. So we went over dehydration, that was in the elimination video, and hydration is actually just the exact opposite of the dehydration mechanism. It's like that for a lot of stuff. The reverse reaction is just going to be the mechanism in reverse. So we're going to start with this double bond. And we have our water, except remember that in the dehydration, it was acid catalyzed. So we're going to start with H3O+. So this is going to act like a base, this double bond. It's going to grab this hydrogen, and it's going to make this into water. And now we have a place to put a hydrogen, a place to put a carbocation. We're going to put the carbocation here and the hydrogen is going to go on there, and I'm not going to show it this time. And now we have water, so here's our water. And this water, I don't need this arrow here anymore. This water is going to attack the carbocation, and that's going to get us this. Now all we have to do is regenerate our acid catalyst by grabbing this proton, and we have our product. And our regenerated catalyst. So that's hydration, exact reverse of dehydration. So hopefully if you remember one, you can kind of cook up the other from that, and you don't have to memorize two things.